Everything we've done so far in the Calculus 2 reproduction list was to prepare ourselves for the concept we learned in this video, and that is the derivative. One of the key concepts in infinitesimal calculus. Let's have a look at these three functions. The first one is f of x equal to the absolute value of x. The second one is f of x is x squared if x is smaller than or equal to 0, and the absolute value of x if it's greater to 0. And the third one it's f of x equal to the square root of the absolute value of x. They all have something in common. All the three functions are continuous in the origin, but they do have something weird going on because it's as if they were all broken in x equal to 0. So when we compare it with this other function, and notice that for this function we can draw tangent lines for every point in the x-axis, like so. So every time I grab a point that is in my function, I can draw the tangent line to the function. And here, for these other functions, if I take, for example, this point, then I can draw this tangent line. Same here. For positive numbers, I can do the same thing. But in 0, there's no tangent line because it comes like this for values near 0, and then when it's negative, it's the opposite. So I don't have a tangent line in the point 0 for the absolute value of x. And the same happens for this one. I can take tangent lines here, but not on 0. And obviously the same happens for this one. I don't know what tangent line to take at 0, but for every other point that tangent line does exist. So there has to be a difference between these functions. How can we define it? So I'm gonna draw an example function. And let's take 2 points in this function and draw the line that shines these 2 points. This is the second line, and we know the slope for this. The slope is going to be if this point here is a and this point is a plus h, this would mean that the difference here is h, so this point would be f of a, and this other point is f of a plus h, so then this vertical difference is f of a plus h minus f of a. We know the slope for this pink line, and that slope from the videos about linear functions is f of a plus h, that is this point, minus f of a minus this point, so we add the height divided by h, divided by the width. So let's see now what happens when, let's say I take again this point initial, and I take h to be a bit smaller. Okay, now h is this different, and this would be f of a plus h. So now the second line is like this. And now I decide I want h to be smaller. Let's say now this is h, this is a plus h, and this value here is f of a plus h. So from these 2 points we have that line. And as we can see from the plot, as h is smaller and closer to a, my slope of the line that joins those 2 points is closer to the tangent line at the point A. So what we are actually doing is turning this into the limit when h tends to 0 of f of a plus h minus f of a divided by h. And so we have a new definition. So we say that a function f is differentiable in A if this limit, the one we were just talking about, exists. And in that case, that is when the limit does exist, we call this limit f prime in A. That is the derivative of f in A. So then what we know from what we just talked is that the tangent line of f at A f of a is the line through a f of a with slope f prime of a. So going back to our previous examples, what we're saying is that if this point is 1, 2 and 3, then the slope for this tangent line is f prime in 1, for this one is f prime in 2, and for this one the slope is f prime in 3. And what we're saying in this case is that at x equals 0, the tangent line doesn't exist. That is, these functions are not differentiable at x equals 0. Let's understand these definitions better with a few examples. The simplest of all functions is a constant, so let's start with that one. We say that f of x is equal to some number c, a constant. Let's plot f for every real number. F of that real number is just c, this number here. So we want to see what the derivative of f is for some point A. So what we have to do is calculate the limit when h tends to 0 of f of a plus h minus f of a divided by h. Now, as our function is constantly c, f of a plus h is c, f of a is c, so we have c minus c divided by h, and the limit c minus c is 0, so then this limit is equal to 0. The limit is 0, and that tells us that the limit does exist. So then f prime in a is equal to 0. And as we didn't take a particular a, we didn't say a was equal to 0 or a was equal to 5, then this is true for every real number a. So the derivative of f is 0 for all a in the real numbers. Which makes a lot of sense, because if we take, for example, this point, a, the tangent line is like this, is like our function. But what is the slope for this? Well, the slope is just 0. It's a horizontal line, and horizontal lines have slopes 0. And the same happens if I take this other a. The slope, again, is 0. So it makes sense for the function to be, the derivative to be 0 for a real number a. Now let's do the same with a bit more complicated function, and that is a linear function. Now f of x is equal to c times x plus d. What is the plot for this? It will be something like this. This would be in the case where c is negative. It would be maybe like this if c was positive, but for the moment let's just assume that c was a negative number. It doesn't matter in the end, but just to be able to make some drawings. And this number here would be d. What we want to do again is calculate the limit when h tends to 0 of f of a plus h minus f of a divided by h. F of a plus h is c times a plus h plus d, and then minus f of a is c times a plus d. All this divided by h, and we are calculating the limit, so don't forget to add it. So now we can do distributively here. This would give us the limit of ca plus ch plus d minus ca minus d divided by h. So we can cancel out ca with minus ca and plus d with minus d. So we have the limit when h tends to 0 of ch divided by h. Now as h is approaching 0 but it's never 0, we can just cancel those out, and then this limit gives us c. So then, again, as I didn't take any particular a, then the derivative of f in a is equal to c for every real number a. And again, this makes sense because if I take this number to be a, the tangent line for this point is the same function. And we know what the slope for a linear function is. That slope is c. So it makes sense for the derivative to be the same number c. So let's move on to a more advanced example. Now we have the function x squared. The plot for our function is going to be something like this. And as we've done before, we want to calculate the limit when h tends to 0 of f of a plus h minus f of a divided by h. So this is the limit when h tends to 0 of f of a plus h is a plus h squared minus f of a squared, all this divided by h. So we can now expand this binomial to get the limit when h tends to 0 of a squared plus 2ah plus h squared. We have minus a squared and all this divided by h. We can cancel out a squared with a squared, and so we have the limit when h tends to 0 of 2ah plus h squared divided by h. Again, we can cancel h, and this limit gives us 2 times a, because here we have plus h, but the h goes to 0, so it leaves us with this term 2a. So what this is telling us is that if I take a number, let's say this point here is 1, and I draw the tangent line. The tangent line for this point will be 2 times 1, that is 2. Now if I grab a point here, 2, and I draw the tangent line for this point, we can see the difference in slope, and for this point it would be 2 times 2, so the slope here is 4. Now if I grab minus 1, here the tangent line first of all is negative. We know this because it's going down, and it would be 2 times minus 1, so it's minus 2. And then minus 2, the tangent line is minus 4, because it's 2 times minus 2. So then f prime in x is equal to 2 times x. This is the derivative of our function. So now I want to talk a bit about the notation. Given a function f, the derivative f prime is often denoted as df dx. That is the derivative of f with respect to x. We'll learn more about this notation and why it makes sense, even though now it might seem like complicated, when we see higher order derivatives and derivatives with respect to other things different to x. But, for example, if I say dx squared dx, it's the derivative of x squared with respect to x. So it's the derivative of f of x equals x squared. Notice that this is notation. So what I mean by this is that d is not an element, a real number. D is just something, it's notation. It's like a delta. We're going to take small pieces of x from our function. So it's not a real number. We can't just do df dx and then cancel the d's. No, we can't. Because it is only notation. Okay, so once this is said, we can just say that the derivative of x squared with respect to x is, as we have calculated before, 2 times x. This is the same thing we said here. So with this new notation, let's see what we know. We saw the derivative of a constant, dc dx, and we said that this was equal to 0. We also saw the derivative of cx plus d with respect to x, and we said that this was equal to c. We just said that the derivative of x squared with respect to x was equal to 2 times x. And what I'm gonna leave you as an exercise is to prove that the derivative of x to the power 3 with respect to x is equal to 3x squared. This will be left as an exercise. So these are all examples of differentiable functions. So it's now natural for us to ask ourselves, are all functions differentiable? Well, let's see a few examples of functions that aren't. The first one is going to think about the function f of x equal to the absolute value of x. in a equals to 0. This function is the one we just mentioned at the beginning of the video. It looks something like this. So what we want to do is calculate the limit when h tends to 0 of f of a plus h, but now a is equal to 0, so we have 0 plus h minus f of a, f of 0, divided by h. This is the same as saying the limit when h tends to 0 of f of 0 plus h is f of h, and that is just the absolute value of h, minus f of 0 is the absolute value of 0 divided by h. So then this is the limit when h tends to 0 of absolute value of h divided by h. So let's go ahead and calculate this limit. Well, as we have an absolute value, we're going to have to do it into two parts. The limit when h tends to 0 from the right, that is positive numbers of h, so the absolute value is just h, and this gives us the limit h tends to 0 from the right of h over h, and it is 1. Now, the limit when h tends to 0 from the left, this will give us negative values of h, will give us absolute value equal to minus h, and then this limit is minus 1. So then we have that the lateral limits are different, and then as we've seen in videos about limits, what this is telling us is that the limit does not exist. And so as this limit doesn't exist for a equals 0, then f of x equal to the absolute value of x is not differentiable at x equals 0. But now, when x is different to 0, then the limit does exist. So that means that f of x, f prime of x, exists. So let's think about our function. The absolute value of x can be written as minus x if x is smaller than or equal to 0, and x if x is greater to 0. So then f prime in x, well, this is just a linear function with c equal to minus 1. So this is of the form cx plus d with c equal to minus 1 and d equal to 0. So we know the derivative for this, and that is c. So in this case is minus 1. And this would be if x is smaller to 0. Not equal, because we just said that f was not differentiable at x equals 0. But when x is smaller to 0, it is differentiable, and the derivative gives us minus 1. And now x is again of the form cx plus d, with c equals to 1 and d equals to 0. So then the derivative of f will be 1 if x is greater to 0. So yes, we have two different values for the derivative, but that's normal, because when we talked about x squared, we also have different values for f prime. That doesn't mean that the function is not differentiable. The function will be not differentiable when this limit doesn't exist, but for these cases, it does exist. And when we look at our function, it makes sense, because if I take this positive number, then here the tangent line has positive slope and equal to 1. And if I grab this number that's negative, then the tangent line has negative slope and equal to -1. So we can try now and plot the derivative of our function. And the derivative will be -1 for all the x that are negative and 1 for all x that are positive. So just pay attention that in 0, this pink function, the derivative, is not defined. Now, this is an example of a function that is differentiable for every x except 0. Now let's look at the second example we talked about. Now f of x is going to be x squared if x is smaller than or equal to 0 and x if x is greater to 0. And let's think about the derivative of this function at x equal to 0. Like before, let's first draw the function. And as usual, let's think about the limit when h tends to 0 of f of a plus h is 0 plus h minus f of 0 divided by h. And this will give us two parts, because f of h will be two different things. F of 0 is always 0, but f of h will be h squared divided by h, because we have here the divided, so this is h, if x is smaller than or equal to 0. And then if x is greater to 0, f of h is h. So then divided by h, this gives us 1 if h is greater to 0. So again, we have a function that's defined in two parts, and we want to calculate this limit. So let's calculate the limit for these two parts, that is the limit when h tends to 0 from the right. That is, when h is greater to 0, our function is constantly 1. So the limit of f of h minus f of 0 divided by h is equal to the limit from the right of 1, and this limit is just 1. And then the limit when h tends to 0 from the left, we're looking at this part, and this is the limit of h. And this limit is obviously 0. So again, these two limits are different, so the limit does not exist. So then this function is not differentiable at x equals 0. However, f prime does exist again for x different to 0, and that is f prime of x will be the derivative of this. So when x is smaller to 0, the derivative is the derivative of x squared, and that is 2x. And when x is greater to 0, the function is defined as x, and the derivative of x is what we said before, it's 1. So then we can draw how the derivative looks for this function. So when x is greater to 0, it's 1, and when x is smaller to 0 is 2x. It's going to be something like this. And at 0, as before, it's just not defined, because the limit doesn't exist in 0 and our function is not differentiable at 0. Now the third example is going to be left as an exercise, and it is the third function we saw in the examples at the beginning of the video. F of x equal to the square root of x, and all you have to do is the exact same thing we have done for our two previous examples. And now the plot for this is something like this. So try and prove why this function is not differentiable at 0 and find the derivative for x smaller and greater to 0, and try and plot it if you can. So now let's finish this video with the first theorem about derivatives. This theorem is extremely important because it's telling us that whenever a function is differentiable at a point, then the function is continuous at that point. So differentiability implies continuity. Let's go ahead and prove it. For continuity, we want to prove that f is continuous at a. We're going to calculate the limit when h tends to 0 of f of a plus h minus f of a. And this is the same as saying this limit but dividing by h and multiplying by h. So this is the limit of f of a plus h minus f of a divided by h, and the limit of the product is just the product of the limits, so this is times the limit of h. So now this first limit exists because f is differentiable at a, and this other limit is equal to 0. So then this is equal to f prime in a, the derivative of f, times 0, and this gives us 0. So then what this is showing us is that f is continuous at a. So we have that differentiability implies continuity. But the converse is not true, because f of x equal to the absolute value of x, for example, is continuous for every real number. But it's not differentiable at x equals 0. So with this very important theorem, we finish our first video about derivatives.